Okay, I'm very pleased to present Mike Waidson, Applications Engineer from Tektronix. And he's going to be talking about Precision Time Protocol. And that is one of the key elements. This is really how we're going to keep all of ST2110 and all of our other media signals working on a modern network. So, Mike, take it away. Let me flip the switch on.
All righty. All right. Does anybody have the time? What time is it? Do you know what time it is now? Time to begin. Yes, it's just after 3 o'clock, 3:06 and 36 seconds, actually. Does anybody have that in nanoseconds? Because I need it in time in seconds and nanoseconds. That's how I'm going to keep time within this system. So we're going to be talking about a variety of things related to PTP and finding out what time it is now and how we keep that time going through the network. And to do that, we're going to be using Precision Time Protocol, PTP, standardized in IEEE 1588. And that sends sync messages periodically that contain the time information. They contain that time information in seconds and nanoseconds, not in 3 hours and 7 minutes now. So how many seconds, how many nanoseconds do we have? And that's all counted from the SMPTE epoch, which was January the 1st at midnight in 1970, when everything was synchronized together at that time. Analog blackburst, digital SDI, and time itself was synchronized at that SMPTE epoch. So in those places, we've got our time, and we're sending that time around. But now we need to do an election process to define who is going to be our master clock within our media network. So how do we elect our grandmaster clock? There are a variety of different settings that you can provide within your sync pulse generator to determine which device is going to be your master clock. And that starts with the priority 1 message that can be configured between 0 to 255. And the lowest number in this game in Las Vegas wins. So if you set the value to 0 of your SPG master clock, then that device would pretty much win unless we go to round 2. And in round 2, it's set by the device. That's the clock class, the clock accuracy, and the clock variance. That depends upon whether the device is internal, locked to GPS, how it's configured. So that's typically set by the device itself. Then you have a priority 2 message, which again has a value between 0 and 255. And so you can get to set that value. And finally, if it's all equal at each of those rounds that we're going to play in a BMCA best master clock algorithm game, then we'll choose the MAC address. And you really don't want to choose the MAC address because that's set by the device and not by you. And you want to have some control over who's going to be the master within the system. So let's play the BMCA game, and we've set up a couple of values for priority 1. We've set a clock class of 6 for our GPS system that's locked to GPS, and we've set a priority 2 value as well. So in our first round, priority 1 is set between the 2 devices exactly the same. So we have to move to round 2. In round 2, clock class between the 2 devices is also set to the same value of 6. They're both locked to GPS. So we have to go to priority 2. And in priority 2, we've got 2 values. Remember, in this game, the lowest value wins. So the lowest value that wins in this case is 64. So this device would become the grandmaster. Let's take a look at another particular case. So in this case, we've lost GPS to this device, but we've locked to GPS on the other device. In this case, priority 1 is again set to 128 for both devices, so the first round is a draw. Let's move on to the second round. In the second round, we have a clock class of 7 because this device was locked to GPS, but no longer is locked. And then we have a device that's locked to GPS that's clock class 6. So in this case, that device will win and become the grandmaster. One more little game. In this particular case, we've got 2 values that are set both to GPS. In this case, we've set the priority of this device over here to 128 and the other device to 64. So in this first round of the competition, this Grandmaster over on the right is going to win. So you get to decide the priority 1 and priority 2 conditions for the devices in your network that are going to be master clocks. And you can choose those 2 values, and the strategy you choose depends upon how you want the primary and backup devices or the third device to be chosen within your master clock. So that's the BMCA game. There are a variety of different message types within PTP. There's an announce message. That message is used to define the best master clock algorithm. So that message contains information about those priority 1 and priority 2 values and the clock class and the clock accuracy and the clock variance. Then we have the sync message. The sync message is containing the time, and that time value is in seconds and nanoseconds. In some cases, depending on the system, we can also follow-up message, which also contains the time. So in that case, we've got 2 types of messages that are going to send the time information. At the receiving device, we're going to send a delay request, because we don't know how long that message took to get across the network for the sync or the follow-up. So we'll send a message out to the master clock through the delay request. And that delay request will meander through the network and be received by the master clock, who will then resend the delay response. So that way we have a known time value between how long it's taken for the message to go in the forward direction and then in the backward direction between those 2 devices. We can also send a variety of different values and configurations within the management message. And the management message might tell us about when to make a jump for our drop frame. It might tell us about daylight savings time. It might tell us all the important things we need to provide sync and timing signals for our broadcast network. So the management message is sent periodically as well to contain that kind of information. And in some cases, we can send signaling information, which tells the system how many times I should send those specific sets of messages. So typically in the system, you can set up how many times you send announce messages, how many times you send sync messages, and that can be configured within the system. And each of these messages goes to typically a multicast address of 224.0.1.129. You can send the PTP messages by unicast as well, but it's only going to be between you and the other device. But in this case, you can see different devices would be able to send those messages either on port 320 or on port 319. When we're troubleshooting PTP, we need to start looking at how we're going to check the different parameters that are selectable within PTP. And there are a wide variety of different parameters that you can set, which then often leads to confusion amongst devices, and then you're wondering why that device is not locked to PTP. So the first thing to do is to check the domain that you're going to decide to use in the system. Each device that is logically connected together should be in the same domain. So we want to group devices together. So we might group all audio devices to one specific domain. Typically, in a media network, we choose one domain value, and that we set to all of our switches within the network and all of our end devices, so that everything is communicating over PTP on a single domain. But if one device is on a different domain when you power it up for the first time, then that particular device will not be communicating with the rest of the PTP domain. So in this case, we've set a value for the domain at 110. So every other device that we want to communicate within this master clock should also be set to 110. The other thing we want to do is check what the Grandmaster ID is. It's useful to know what the MAC address is of each of your master clocks, because that is what is sent as the Grandmaster ID. So if you know your primary and backup master ID, then you'll have an idea of which device is sending the signals at a specific time. You also want to check those message rates. So in SMPTE 2059, those message rates are sent at 4 times a second for announce and 8 times a second for sync and delay request and delay response typically. So it's important to check that those values are coming at the same periodic rate. You can see in this case, the value says infinite, which means we haven't seen any delay responses on this network. So that means there have been no messages from the master to the end device, which is being used in this case. So we have a communication problem within part of this network in this case. Although we're receiving announce and sync messages, we can time, but it won't be as accurate as if we use delay request and delay response. So ensuring lock in our particular device, we're using a Prism to be our end device. We've set it up to that domain 110, and then we've been able to achieve a lock and gather the time information. It tells us the grandmaster ID of the master clock, and it tells us the priority messages for those priority 1 and priority 2 values that are being sent by the master clock system. It also provides us with information on those announce rates, delay request and sync, and delay response messages. So in the SMPTE profile, as I mentioned, there's 4 announce messages per second and 8 delay request, delay response, and sync messages that are being sent in this case. There's also a value which shows you how many steps are removed from the system. So it's possible that you could go through multiple switch configurations, in which case the steps removed would increase by the number of switch configurations that the PTP messages have passed through. So one of the important things to do when you're looking into PTP is to make sure that all of your devices are on the same domain. So we can look at the PTP messages within the system and pick out that all of these PTP messages that are coming through are all on the same domain. If you just power on a device, it might come at its default domain value, which might not be your system domain. And then it won't see the master clock, which is on this 127 domain in this case. It'll try and communicate with another domain that won't maybe exist. And then you wonder why that device isn't locked to your PTP system. So it's important then to make sure that you're using a specific domain, and that domain is configured for each device within your network. You also want to make sure to check those MAC addresses, because these are the MAC addresses of that grandmaster ID. So these are the grandmaster ID that we're using, and these are MAC addresses maybe of a switch or other device within the system. So that way you can check the MAC addresses of the devices too. Sometimes when we are looking at the grandmaster ID, we might see one value, and then all of a sudden the next second we'll see another value. And then the next second later, we might see another value. And so we might get this toggling between the grandmaster IDs. So then it becomes the difficulty of trying to troubleshoot what's actually happening in these cases as we're toggling back and forth between these grandmaster IDs. What's typically happening is there is a timeout value that happens. So if a device hasn't received an announce message after a period of 3 timeouts typically, or 3 periods, then in that particular case, the best master clock algorithm will start to go again. And so that made this have to look for another device to become the grandmaster. And so that's when you'll start to see this toggling effect happening between the 2 devices, as they'll go back and forth between the masters, as one tries to take over from the other. Typically in this case, you need to check those message rates. Make sure they're exactly the same across the network for all devices. You want to make sure of what your timeout value for the announced message is set at, which is typically 3. And you want to check for loops within the network, because maybe those messages are somehow making their way around and back to the grandmaster, causing an election process to happen again. So in those cases, you want to be careful, and if you see this kind of condition happen, then just be aware that either you need to check announce messages or you need to check timeout messages within those configurations. In the Prism, we can graphically plot the PTP configuration of the messages. So we can see over time what's happening to the master to slave delay and the slave to master delay, the forward and reverse pass of the communication messages between delay request and delay response. Ideally, in a perfect system, those values should basically converge together, so they should be almost identical within the system. We also have the phase lag value, which is shown over in the top right there. That is a combination of the forward and reverse pass and a filtered response. And again, the lower that value is, the better and more reliable your PTP will be. The more larger that value, the more likely is you've got additional jitter in the network. Maybe you've got a wider variety of different traffic going across the network. Maybe you're getting close to becoming unlocked within the system. So a nice low value for the phase lag will ensure you have a nice, robust PTP system. Typically, in a PTP system, we have a typical network topology, which will include a variety of different network switches that will be PTP aware. Devices that are PTP aware know how to process PTP messages. And there are two types of switch configurations that can be done. A transparent switch. If you configure a device to be a transparent switch, what it will do is it will configure the system and calculate how long it takes for the PTP message to come into the network and the switch, and how long it takes to get that message out of the port. So it will calculate a value for the time it takes to process that message from the incoming port to the outgoing port. And it will then add a correction factor. In some of the switches, it requires to do that time synchronization in a follow-up message to calculate the correction factor. So that becomes a two-step process, and that's why we have a sync message and then a follow-up message to do that two-stage process where they add the correction factor to the second message for the follow-up. So a transparent switch will take account of the network delay through the active device. Another case will be in the case of a boundary switch. So here, as the name implies, we're creating a boundary between the master devices and the end devices within the system. And so the grandmaster will be talking to the switches that are set up in boundary mode, but he'll never talk to the end devices. So communication will always be between the master and the switches set in boundary mode. The switches themselves will then provide the PTP messages to all the end devices on their ports, creating this boundary between the grandmaster and the end devices. So the end devices in this case will never talk to the primary. This is a way to rationalize some of the message rates that we're sending. So we're sending announce messages, we're sending sync messages, delay request, delay response. If there are one device, that's not many messages to send. It's a little eight messages every second, a very low rate. But when we get 1,000 devices that are sending those same kind of messages, all of a sudden the message rate starts to become more increased. So if we can keep our grandmaster boundary to the rest of the switches, then it's going to only have to deal with all the switches connected to the network, and it'll never have to communicate with all the end devices, and therefore we can reduce the amount of traffic for all those delay requests and delay response messages that we're sending across the network. So that's one strategy of streamlining the amount of messages between all these end devices and the grandmaster, so that the grandmaster is only talking to the boundary switches in this case, and never really talks to any of the end devices. So these are kind of strategies you can use for PTP-aware switches to assist in the traffic flow of PTP messages across the network. In the switch itself, you can also find out information and to check configurations to ensure that you are locked to the correct master. So you can use commands like show PTP, which will show all of the ports and how are they configured. So you'll find out in this configuration that one of those ports is set up as a slave port. So that means that this particular switch is set up in a boundary mode, because it's got one port that is locked to the grandmaster, and then the other ports are all master ports that are enabled. or active within this switch. So we can see that this is in a boundary clock mode, and these are the specific ports that have been enabled to receive PTP messages. Then we can also do a couple of other particular pieces, which is to show the PTP clock. In this case, we'll get some other kinds of information relative to the grandmaster, the number of ports in slave, and the number of ports that are active for PTP messages, and where they're configured. So you can get information about the PTP and the way the switch is configured within some of these basic particular parameters that you can type in to the command line for the switch. You can also go to each individual port that's enabled with, for instance, a boundary clock, and actually show the messages that are present for the interaction between the channels. So you can check that you're receiving announce messages, you're receiving sync messages at specific rates, you're receiving delay request and delay response messages. So if you weren't getting the delay request and delay response messages, then that's a problem, because the device is not fully communicating in PTP. But if you're seeing those delay request and delay response messages actually happen, then in that case you should be able to lock to PTP with your end device. And so you've got different switches will give you that information slightly differently. So here is a particular device giving that same kind of counter messages for your delay request, delay response, sync, and announce messages. And periodically you can ask it to refresh that information to see that it's actually updating time and time again. So that's the way you can specifically choose the information relative to ensuring that you have PTP enabled across your ports and that your switch is typically set in boundary mode. So the question now is, what time is it now? Okay? So we got to our 3:30 deadline, just a few minutes early. So we get time for a couple of questions, and if anybody's got any questions.
Okay, if you have a question, just let me know, raise your hand, or I'll bring the microphone over. So what time is it now?
It's 3 o'clock.
Okay. You
And
have
28.
a GPS receiver?
No, I don't have GPS. I have an atomic clock here, though.
Ah, cool, cool. All right, any questions, anybody? Yeah, hold on.
When you have a mixed environment of video and audio equipment, the audio equipment, Dante, AES67, that's different from, well, that's running on IEEE 1588 version 2, and then you've got the video gear running at 2059. What's the optimal set of switch settings for delay and so forth that would allow a 2059 PTP to lock Dante and other AES67 equipment and devices?
Okay, so there's a profile for AES67 for the timing configuration that is different than the SMPTE 2059. So the AES standard R16, I think, establishes kind of ground rules for having a profile which is an intermix of the two. So it establishes like a domain 0, which is used for audio. That's the domain that we would establish between our media network and our AES audio network within those particular cases. So there are rules and guidelines that not only then allow you to kind of coalesce the two together. So announce messages, typically like we run at the interrupt, we use announce messages at 1 second, because that's the period that is established within the R16. And then we have the sync messages and other particular running at 8 per second. So that's a homogenized version of AES67 profile versus the SMPTE 2059 profile. For Dante devices itself, that's a slightly different thing, because most of those devices run on version 1 of PTP and not on what the rest of the media network would be running, which is currently on version 2 of PTP. So you have to have some way to translate those two particular devices between those domains. So if you're in AES67 or you have a way to transpose the Dante into AES67, then that should be locked to the media clock and to the PTP version 2. But you might need an additional clock to run PTP version 1 somewhere else in the network if you're doing that. Okay?
Any other questions? Okay, Mike, thank you very much.
Thank you.